Welcome to the second of 3 web seminars about transforming fluid power. Today we will be talking about transforming pneumatics by rethinking the power formulas, velocity control, and eliminating restrictive flow controls. My name is Dan Helgerson. Flow means go. Well, not exactly. It is not that we need to learn new things. We simply have to think more deeply about the things we already know and have sometimes taken for granted. One of the most common misunderstandings about fluid power is the relationship between flow and pressure. It is hard to convince someone that increasing the pressure in a system will not increase the speed when the technician just finished increasing the pressure and things are going faster. If the system in question has restrictive flow controls, or even if it only has plumbing that functions as a restrictive orifice, increasing the pressure upstream from the restrictions will increase the flow to the actuator. It was the increase in flow resulting from the increase in pressure that made things go faster. Without sufficient pressure and an open pathway, there is no flow and so no go. If you were to ask a pneumatic professional how to make a motor or a cylinder go faster, you would likely receive the answer, add more flow. This is normally my answer too, especially when doing training in basic fluid power. A fixed displacement actuator, be it a motor or a cylinder, will require a certain volume of fluid to move a given distance. The rate of speed is determined by the flow rate to the actuator. If someone were to suggest to us that we could slow down a cylinder by increasing the pressure, or speed up a motor by increasing the displacement, we would likely reject that notion immediately. With hydraulics, the reasoning behind this concept is pretty straightforward. The relative incompressibility of the fluid dictates that if a volume of fluid is needed to extend a cylinder, then the linear velocity is determined by the rate at which that volume enters the actuator, regardless of the pressure required. A pump that supplied 20 liters per minute would fully extend the cylinder in 3 seconds, regardless of the pressure required. With pneumatics, it is not quite that simple. Compressors are rated in volumes of free air per minute, normal liters per minute or standard cubic feet per minute. If the flow from a compressor rated at 20 normal liters per minute was sent directly to the cylinder, there is no telling what the velocity would be without knowing the required pressure. The actuator would have continuous change in velocity as the load varied. The compressibility of air completely changes the way we must think about flow and pressure. While 1 unit of hydraulic fluid fills about the same volume whether it is a low or a high pressure, 1 unit of free air is reduced in volume as the pressure increases. The flow of free air to the cylinder is constant, but the flow in volume is diminished as the load increases. As the pressure increased, the flow in free air stayed the same, but the flow in volume decreased. When a receiver is added to the circuit, source flow is directed to the receiver until the set pressure is reached. The pressurized air can be sent to the cylinder, which begins to rapidly extend, but slows as the resistance builds. The cylinder cycles faster, but we still do not have true velocity control. Reducing pressure, a way to save or waste energy. This is the title of an article that was in the Fluid Power Journal, and the article explains the difference between a hydraulic pressure reducing valve and an air pressure regulator. The actuator in a hydraulic system needs a fixed volume of fluid to move a given distance. The pressure is determined by the resistance to that flow. The pressure-reducing valve squeezes off any extra pressure to reduce velocity and force. Pressure-reducing valves do not limit the amount of energy used. They merely limit the amount of energy that gets to the actuator. The pressure in a volume of air is determined by the number of air molecules in that volume. The pressure is raised by adding more molecules to that volume. With pneumatics, then, by definition, the pressure regulator limits the number of air molecules that are allowed to pass through. The pressure regulator reduces the energy that is used. In both hydraulics and pneumatics, a flow control limits the speed at which the energy flows, not the amount of energy that is used. We will look a little more closely at the effect of changing the displacement of or pressure to an actuator. Energy that is stored in a receiver or coming directly from the compressor is always at a pressure that is higher than what is required for the load. If it were not, nothing would move. The extra pressure produces unwanted acceleration, and so we find ways to skim off the extra pressure to get the volume of fluid we need at the rate we require. We are so accustomed to this concept that we take for granted the need to toss away the excess energy supplied from the compressor or receiver. The energy loss is simply the cost of control. The power formula for angular velocity. We know the equation for power when given torque and RPM. We know the equation for torque when given displacement and pressure. We can combine the two equations to solve for angular velocity using displacement and pressure and power. We get a new formula where RPM is a product of power times a constant divided by the pressure times the displacement. The power formula for linear velocity. Again, we know the equation for power when given flow and pressure. We know the equation for flow when given diameter and linear velocity. We can combine these two equations to solve for linear velocity using diameter, pressure, and power, where we find velocity is equal to power divided by the diameter square times pressure times a constant. We will now refer to our power formula as our velocity formula, and we will look at it for both angular and linear velocity to see what we can learn. If we remove the constants, we find that velocity is proportional to power, pressure, and displacement. There is an inextricable relationship between pressure and flow that must be understood when we are talking of fluid power transfer. For any given RPM requirement, at a given power, there must be a discrete product of pressure and displacement. For any given velocity requirement at a given power, there must be a discrete product of pressure and diameter square. When velocity is used as the primary control, the equations can be solved with some surprising results and some new opportunities. Let's try it out for angular velocity. We will solve for RPM. For power, put in 0.25 kilowatts. K is 60,000 from the earlier formula. For pressure, put in 0.6 megapascals, and the displacement will be 10 cc's. When we solve this for RPM, we get 2,500 RPM. Now, change the pressure to 0.7 megapascals. When we solve this for RPM, we get 2,143 RPM. An increase in pressure caused a decrease in RPM. At first, this is counterintuitive. An increase in pressure would cause an expectation of an increase in flow. But in these equations, we only changed the pressure. The power and displacement stayed the same. So let's try it out for linear velocity, and again we will solve for a velocity. For power, put in 0.25 kilowatts as before. For pressure, again put in 0.6 megapascals. The diameter will be 50 millimeters, and K is a constant of 0.000783 from the earlier formula. When we solve this for velocity, we get 0.213 meters per second. Now, change the pressure to 0.7 megapascals. When we solve this for velocity, we get 0.182 meters per second. An increase in pressure caused a decrease in velocity. Again, this seems counterintuitive. An increase in pressure should cause or would cause an expectation of an increase in flow, but in these equations, we only changed the pressure. The power and diameter stayed the same. According to the velocity formula, if air is used to drive a fixed displacement motor under constant load, you could establish the motor RPM by the pressure setting of the regulator, without the use of a restrictive flow control. With a fixed displacement motor, if power, pressure, and displacement are constant, then RPM must also be constant. A constant power input at a constant pressure with a fixed displacement must yield a constant RPM, and the same is true for a cylinder. A constant power input at a constant pressure with a fixed displacement must yield a constant velocity. We need to think differently. Instead of separating flow and pressure as two different entities, we need to combine them into a single unit of power. Much like in electricity, where the volt-amp is the unit of power, we need to think in terms of pressure flow, PQ, as our unit of power. 1 megapascal times 1 liter per minute could be 1 megapascal liter per minute unit of power. 1 unit of power can be made up of 0.1 megapascals at 10 liters per minute, or 2 megapascals at 0.5 liters per minute. Or we had 1 psi times 1 CFM equals 1 psi CFM unit of power. 1 unit of power can be made up of 10 psi at 10 CFM, or 200 psi at 0.5 CFM, or any combination of pressure and flow that equals 1 pressure flow unit of power. Stored energy should also be thought of as a volume of energy units, pressure times volume. 1 cc at 1 megapascal equals 1 cc megapascal unit of energy. One energy unit can be made up of 10 cc's at 0.1 megapascals, or 0.5 cc's at 2 megapascals. Or 1 cubic inch at 1 psi equals 1 inch-pound energy unit. One energy unit can be made up of 10 cubic inches at 0.1 psi, or 0.5 cubic inches at 2 psi. Or any combination of volume and pressure that equals 1 pressure volume energy unit. A receiver holding 50 liters at 0.5 megapascals has the same potential energy as a receiver holding 25 liters at 1 megapascal. When we think this way, we are closer to finding a way to use flow, but not at the expense of pressure. We can determine power requirements in terms of units of pressure times volume. We can understand the potential energy stored in receivers and hopefully not be too willing to toss the excess away. Using stored energy. Here we have a receiver. It is 12 inches in diameter, 48 inches tall, and we're going to charge it to 125 psi. How many cubic inches are in the receiver? Well, 12 inches square times 0.7854 times the height of 48 inches equals 5,429 cubic inches. What is the potential energy in the receiver? Multiplying the fluid volume by the pressure, we get 5,429 cubic inches times 125 psi equals 678,586 inch-pounds. Each cubic inch has been charged with 125 psi to provide the stored energy, potential energy, of 678,586 inch-pounds. The energy will be used to move a load in and out. We're assigning a load of 800 pounds of resistance to a cylinder with a 1-inch rod, a 4-inch bore, and a 12-inch stroke. How much pressure would be required to extend this cylinder? Well, we take the 800 pounds and we divide it by the area of the piston, and we find that what will require will be 64 psi to extend this cylinder. What will be the pressure to retract the cylinder? Well, we use the same math equation here, except now we have to take out the area of the rod, and so we find that we're going to have a little bit higher pressure. It will be 68 psi. The volume to extend is 150.84 cubic inches. The volume to retract is 141.42 cubic inches. That means we have a total of 292.26 cubic inches required. We want the cylinder to extend and then retract in 2 seconds. So when we shift the valve, we find that this is what we want. We want it to extend out in 2 seconds. We then want it to retract in 2 seconds, and things seem to be doing very, very well. However, what is really going to happen here? We shift the valve and, whoa, that goes out fast. And also note the drop in pressure and in the potential energy. We shift it again and, oh, it goes really fast back. There is more force than is required, and the force translates into acceleration, extending and retracting in about 0.6 seconds. So what do we do? Of course, we add flow controls. We call them flow controls, but they're actually power controls. Now when we shift the valve, we get it to extend in 2 seconds. We shift the valve back. We get it to retract in 2 seconds, and now we're pleased that the cycle time is correct. But there was too much pressure available, and the velocity needs to be limited. The power controls add a resistance, increasing the force requirement for moving the load. The extra energy is consumed as the air moves across the flow controls. How much of our potential energy was used to move the 800 pounds, a total of 24 inches? Well, we had 292 cubic inches of air that was consumed, each charged with an average of 122 psi. So 292 cubic inches times 122 psi equals 35,624 inch-pounds. Now, only 800 pounds at 24 inches, or 19,200 inch-pounds, was needed to do the work. In order to control the power, the rate at which the work was done, a resistive load was added to counteract the excess acceleration. The meter-out flow controls added an additional load of 766 pounds extending and 729 pounds retracting, so that the full 122 psi at 292 cubic inches, or 35,624 inch-pounds, was used. There was enough energy stored in each cubic inch so that only 157 cubic inches were needed to do the work. 35,624 inch-pounds of energy was used, while 16,424 inch-pounds was tossed away across the power controls. There was enough energy stored to extend and retract the load 35.35 times, but the power controls consumed so much energy that the receiver capacity could only cycle the cylinder 10 times. The system is only 28% efficient. the constant load gave the appearance of velocity control, but this would not be true with a variable load and or a variable pressure. Is there a way the excess pressure could be transformed instead of tossed out so that less energy could be drawn from the source? What if we could have actuators only draw the power needed to do the work at the required speed? Divide and conquer. Understanding the displacement transformer. Now, in fairness here, the picture that I have is certainly a hydraulic flow divider, and to my knowledge, we don't have anything quite like this right now in pneumatics, but for all practical purposes, what we have is a positive displacement turbocharger. The device is made up of 2 or more separate fixed displacement motor compressors that are mechanically connected. In our discussion, we will refer to them as fixed displacement transformers, or FDTs. The most common symbol for the FDT is a group of fluid motors, in this case 2, that are touching, as in figure 1. Because the device both drives and is driven by the fluid, a more accurate symbol is shown in figure 2. It can be both a motor and a compressor, and this is the symbol we would use in our discussions as we move forward. When flow enters the FDT at one side, it is divided proportionally based on the displacements of the sections. The sum of the power exiting will equal that of the power entering. For example, with a 2-section device of equal displacement, if 20 normal liters per minute at 0.8 megapascals exits from one port and 20 normal liters per minute at 0 megapascals exits from the other port, a total of 40 normal liters per minute will have to enter at a pressure of, you got it, the input pressure would be 0.4 megapascals. Power in equals power out. 40 normal liters per minute at 0.4 megapascals equals 20 normal liters per minute at 0.8 megapascals plus 20 normal liters per minute at 0 megapascals. We will take a look at several potential applications of the FDT. We will limit our descriptions to devices with only 2 sections. The examples are not intended to be fully operational circuits, but are ways that the transformers could be configured. First of all, of course, is a flow divider. We have an input flow, and we've divided the output flow on 2 sides. Now, hydraulically, this is something that could be used to synchronize 2 equal area cylinders. However, pneumatically, this would not be the case. If we had a different load on each one, we would still have the compressibility of the air to deal with. So this is simply showing the ability to divide the input air flow. Pressure intensifier. Here we have an input flow where I'm taking one side of the FDT and I'm returning it to atmosphere, and that enables me to have an intensified pressure at a reduced flow. The advantage here is that it's a continuous operation, and with varying displacement ratios, we could have pretty high pressures at a constant rate without the reciprocating action of a cylinder, which is the typical pressure intensifier. A flow augmenter. Here's a situation where we're using the upper unit as a motor to drive the lower unit as a compressor. And so we have an input flow, then we're drawing air into the lower unit, and we have an augmented flow at reduced pressure. So we would have twice the flow going out, again, assuming this is a equal displacement units, we would have twice the pressure coming, twice the flow coming out at half the pressure. 2-speed, 2-force cylinder clamp. The 2 flows from the FDT are combined through the directional valve until the cylinder meets a set resistance. The increase in pressure pilots the directional valve, exhausting half the FDT flow to atmosphere, doubling the pressure and force of the cylinder. A 2-speed, 2-force motor. Here we have a very similar circuit, except we've replaced the cylinder with a motor. The two flows from the FDT are combined as before through the directional valve until the motor meets a set resistance. The increase in pressure pilots the directional valve, exhausting half the FDT flow to atmosphere, doubling the torque and reducing the speed. Regenerating motor circuit. How can you regenerate an air motor? Well, let's take a closer look. When the directional valve is in the pictured condition, all flow from the transformer passes to atmosphere. The motor speed is determined by the source flow. When the directional valve is shifted, half the flow goes to the atmosphere while the other half joins the source flow. The motor has half the torque and may go twice as fast without changing the source flow. Transformation complete. Now, an FDT is not really a flow or power control. It is a flow divider combiner. It splits or combines energy units in proportion to the ratios of the displacement sections. It does not limit flow, but merely proportions whatever power is passing through. What is needed is a way to use the transforming powers of the FDT to mold the transfer of energy in a way that will provide true power control, not just flow control. What we are about to see is a new displacement device that will enable us to let each actuator draw only the energy units needed for the work being done. When we think of power as a rate of energy unit input, we can see how controlling that energy can provide speed control without the use of restrictive flow controls. Introducing the Variable Displacement Transformer, or the VDT. The VDT is simply a single, two-chamber, positive displacement device with the displacement of each chamber dependent on the displacement of the other. It is placed in the fluid stream in such a way as to divide or combine energy units, much like the FDT on the previous slides, only with infinite variability. It can proportion the energy into 100% to 0%, or from 0% to 100% ratio, or anything in between. The suggested symbol on the right shows a single rotary device with two chambers. Each one is dependent on the other, and each one can be driven by or drive the fluid energy passing through it. It is also infinitely variable. We will take the earlier example of the motor regeneration circuit, but replace the FDT with a VDT and require a constant RPM. The motor exhaust is directed to the VDT inlet, where it is divided between the chambers of the transformer. An adjustable orifice sets the pressure drop that controls the compensator of the VDT. The source pressure will be set at 0.7 megapascals. The fixed motor displacement is 100 cc's per rev, and the required speed will be 1200 RPM. The default condition of the VDT is for 100% of the flow to exhaust from port P4. Port P2 joins the flow line from the source. What will be the flow in normal liters per minute required to achieve 1200 RPM from the motor? The compression ratio at 0.7 megapascals is 7.93 to 1. The liters per minute required will be 1200 RPM times 100 cc's divided by 1000 cc's per liter equals 120 liters per minute. Multiplying the compression ratio times the 120 liters per minute tells us that we are going to require 952 normal liters per minute in order to maintain 1200 RPM on this motor. That means that we will be entering the motor with 952 normal liters per minute. It also means that I will be drawing from my source 952 normal liters per minute, at least at the beginning. I'm going to have an exhaust flow of 952 normal liters per minute. I will have an exhaust from P4 of 952 liters per minute, and I will have zero flow coming from P2 because all the flow is going out the exhaust port P4. What will be the pressure in the line from P2? Well, as you can see, line P2 is connected to the source line, and so therefore we know that the pressure there is going to be 0.7 megapascals. The torque that we're going to have in this condition we can find by using the formula, and we find that we have a torque of 11.1 Newton meters. So at 0.7 megapascals and 1200 RPM and 100 cc's, we will be drawing 1.4 kilowatts of power, and we will be at the maximum torque capability of this motor. Now notice that as the torque begins to diminish, what will happen is that the motor is going to try to accelerate. As it tries to accelerate, it's going to have an increased exhaust flow. That increased exhaust flow is going to cause a greater pressure drop, which is going to cause the compensator to modify the condition of the VDT, and it's going to reduce the amount that is exhausted to atmosphere, and it's going to send some of the flow back into the fluid stream to the motor. So here we have, we've reduced the flow from the port P4 down to 816 normal liters per minute, and we have added 136 normal liters per minute into the source flow. But as you can also see that we have reduced the flow that we have coming from our source, which now been reduced to 816 normal liters per minute. Now as the torque continues to diminish, we see that the VDT continually responds, providing a resistive load so that the actual torque capability has been reduced, but the effort to do that is taking the energy and putting it back into the source flow. So as we move down through here until we get down to our minimum torque, we find that we have only 136 normal liters per minute coming from our source, but I continually have 952 normal liters per minute coming into the motor. That is what the VDT does for us. What it does is it takes the extra energy that we would usually waste through a meter out flow control, and we feed that energy back into the inlet circuit. Will the VDT work on a linear device? Well, the power formula for linear motion should tell us. We'll shake it up in our equation mixer and come up with our new formula solving for velocity. And what we find again is that for any given power requirement at a given velocity, there must be a discrete product of pressure and displacement. The fixed displacement motor has been replaced with a cylinder and a directional valve. The cylinder has a 112 millimeter bore, a 1 meter stroke, and a 50 millimeter rod. It will travel at 0.21 meters per second. At 0.7 megapascals, it has a maximum possible force of 5,522 newtons. The airflow volume will be 100 liters per minute, and with the 7.93 compression ratio, the flow to the cylinder will be 793 normal liters per minute. That means we'll also have to have 793 normal liters per minute being drawn from our source. It means that our exhaust flow will be 793 normal liters per minute, and our flow out of port P4 will be 793 normal liters per minute, and we will have zero coming in through port 2 into the power line. Now when we look at the formula, we see that at 0.7 megapascals and at that particular velocity and with that pressure, we are going to have to draw 1.16 kilowatts of power. Now watch, as the load varies, the source pressure remains the same, but the VDT responds, sending the extra energy units back into the source line. So as we reduce the load, what happens is I get more and more flow coming back into the source line. And the fact is, a fixed displacement actuator, whether a motor or a cylinder, will have a discrete exhaust flow for any given velocity. This exhaust flow, passing through the orifice and then through the transformers, is used to control the velocity. There is no need for the restrictive flow control. Transformation application. If you would like to try out a VDT, you may have to wait a bit. A pneumatic version of the VDT is currently under development. It consists of a rotating vane group within an elliptical chamber, as in the 3D printed example to the right. Its operation is illustrated on the next slide. Using a balanced vane system, a series of vanes fitted into a rotating hub, driven by inlet flow and pressure, are spun in a movable elliptical chamber. The spinning vanes produce a compressing action as they move to and from the apex of the chamber. There are 2 compressing events for each revolution. As the elliptical chamber moves, it causes a change in the displacements on both sides, establishing percent ratios between 100 to 0 or 0 to 100. 2 pilot ports and a spring make up the control for the output flow. A ported cover plate provides the inlet and outlet flow paths. The cross port between the inlets provides pressure to hold the vanes against the wall of the chamber. The inlet flow at ports 1 and 3 is divided between the outlet ports 2 and 4. The VDT can also be used as an adjustable fixed displacement transformer, FDT, by adding an adjustable screw. As the elliptical chamber is adjusted, it causes a change in the displacements on both sides, establishing percent ratios between 100 to 1 and 0 to 100, 100 to 0 and 0 to 100. This provides manual adjustment to some fixed position for proportional flow division, flow augmentation, or pressure intensification. The inlet flow at ports 1 and 3 is divided between the outlet ports 2 and 4, and about a 50-50 split is shown here. If the VDT and adjustable FDT do not yet exist, then why are we talking about them? Well, we have learned in this seminar that we need to think differently. We need to think in terms of energy units and units of power. This enables us to better define system efficiency by comparing actual work accomplished with the energy being consumed. And we will view the restrictive flow controls for what they really are, power parasites. We will recognize pressure regulators as real energy savers. And as we become more aware of the inefficiencies, we will be looking for solutions. When the VDT becomes available, we will be ready to embrace it. So go back and look at the applications for the FDT that were shown in the earlier slides. Remember, we said we need to think differently. Review this material. Check the math. Analyze the circuits. Think differently. So, what do we take away from this presentation? Think in terms of energy units and units of power. Think of the receiver as a storage warehouse for energy units. Determine the actual work to be done and the energy units needed to do that work. Design so that as few energy units as possible are consumed for control. Consider the VDT as a possible solution. We covered a lot of material in this presentation, maybe too much. This and other presentations can be revisited from the IFPS website. You can then view them at your own pace. You may request a free copy of the series of articles about transforming fluid power that appeared in the Fluid Power Journal by going to danhelgerson.com/webinar. To send questions or comments, please go to danhelgerson.com and select the Contact tab at the top of the home page. Thank you very much for your attention. Do you have any questions?